Today we start with Jordan canonical form. In this we will study introduction to Jordan canonical form of modeling, state space representation of Jordan canonical form of modeling and numerical example. Now introduction to Jordan canonical form of modeling. The state model having repeated roots in the denominator is called Jordan canonical form. Last time we have studied diagonal canonical form. Diagonal canonical form means that eigenvalues are distinct, they are not repeated. Here we are considering the case where eigenvalues are repeated. So that type of model is called Jordan canonical form. This method is based on concept of partial fraction expansion. Similar to canonical form of modeling, that is diagonal canonical form, this type of modeling is based on partial fraction expansion, and you know that why it is required, because it is not possible to determine the inverse of such type of equations. So in order to determine inverse properly, we need to do partial fraction expansion. This form is useful in state space analysis, controller design, and also in model order reduction techniques. See here, whenever we are learning any form, it has some applications. As I have told last time that canonical form, that is diagonal canonical form, is useful in checking controllability, observability. So this type of form is also useful in checking controllability, observability, and also it is used in model order reduction technique. Last time I told what is model order reduction? The model which is higher order, which can be reduced to smaller size, for that also this Jordan type of technique can be useful. Now we start with representing any system in Jordan canonical form. For that purpose we write equation as y of s divided by u of s, that is equal to b3s cube plus b2s square plus b1s plus b naught divided by, we write as s cube plus a2s square plus a1s plus a naught. So this is third order system, and you will find that here order of the numerator is also 3. So this is a proper transfer function, and we assume that the roots of this denominator are repeated. That means the eigenvalues, or we can say roots of this denominator is repeated. Therefore we write this equation as y of s by u of s equal to b3s cube plus b2s square plus b1s plus b naught divided by s plus lambda 1 square plus s plus lambda 3. Here s plus lambda 1 square, that is there are two roots that are repeated, and now another root is s plus lambda 3. Now finally we write this equation as y of s equal to b3s cube plus b2s square plus b1s plus b naught divided by s plus lambda 1 square into s plus lambda 3 into u of s. Now here this type of transfer function we cannot apply inverse Laplace transforms. So in order to apply inverse Laplace transform, this transfer function we have to write in this form as b3 upon c1 s plus lambda 1 square b3 into u of s, here u of s, then here c2 s plus lambda 1 into u of s plus c3 s plus lambda 3 into u of s. So ys represented in terms of b3, c1, c2 and c3. c1, c2 and c3, they are called residues. So now what you do, we can represent this transfer function y of s, that is equals to b3 into u of s plus c1 into x1 of s plus c2 into x2 of s plus c3 into x3 of s. So, what we have done here, this u of s divided by s plus lambda 1 square we represent it as x1 of s, then this u of s plus lambda 1 we represent it as x2 of s, and this u of s divided by s plus 3 we are represented by x3 of s. Now here y of s, but we have a state space model, that is we require state space model. That state space model is to be in a time domain. That means for these equations we have to apply inverse Laplace transform. So in order to get the model, what we do, we will consider each element, that is x1s, x1 of s, x2 of s and x3 of s separately. So now we write x1 of s that is equals to u of s divided by s plus lambda 1 square. Now x2 of s that is equal to u of s divided by s plus lambda 1, and finally x3 of s equal to 1 plus s plus lambda 3 into u of s. So we have written x1 of s, x2 of s and x3 of s. Now we want a state space model. As far as this x2 of s and x3 of s we considered, if you consider this x2 of s and x3 of s, we will find that directly we can multiply and we can get the model in time domain. But there is a problem with x1 of s because s plus lambda 1 square is there. So it is difficult to apply right now the inverse Laplace for this equation. Now how to tackle this? So one possibility is that what we do, we can divide this x1 of s and x2 of s. So if you divide this x1 of s divided by x2 of s, so if we actually divide it, what will happen, u of s divided by s plus lambda 1 square divided by u of s divided by s plus lambda 1. So this u of s will cancel and one term of s plus lambda 1 will cancel, and finally we will get 1 upon s plus lambda 1. Now what we do, we can do some cross multiplication. So what we will get, after doing cross multiplication we will get s x1 of s plus lambda 1 into x1 of s equal to x2 of s. Now here we apply inverse Laplace transform. So x1 of s, that is x1 dot equal to, now we shift lambda 1 x1 of s into right side, what we will get? We will get minus lambda 1 into x1 plus x2. So this is the first state equation. This, let us say, equation number 1. x1 dot equals to minus lambda 1 x1 plus x2. Now this x2 of x3s is simple, so we can write this as x3 of s equals to u of s plus lambda 1. So if you solve it, what will get? We will get s into x3 of s lambda 1 into x3 of s into u of s. Now what we do, we can do it, that is x3 dot, sorry, x2 of s, we can write x2 of s u of s plus lambda 1. So we will get x2 of s here lambda 1 into x2 of s equals to u of s. So what we will get here, x2 dot equals to minus lambda 1 x2 plus u. So what we have taken? We have taken x2 of s equal to u of s by s plus lambda 1. So we cross multiplied it, x2 of s plus lambda 1 into x2 of s equals to u of s. So inverse Laplace, we will get x2 dot minus lambda 1 into x2 plus u. So second equation we have got, so we write like this. This is equation number 2. Now about third is x3. So here x3 of s equal to u of s divided by S plus lambda 3. So, how you write this equation? Again we cross multiply it, S x3 of S plus lambda 3 x3 of S equal to u of S. So, we got x x3 of S, lambda 3 x3 of S plus u of S. Here also we apply inverse Laplace transform. So, what we will get? We will get x3 dot equals to minus lambda 3 into x3 plus u. Now, what is the output equation? Now, output equation is, now after this we have to determine the state space model. It can be written as x1 dot, x2 dot, x3 dot, that is equal to, what is x1 dot? X1 dot equals to minus lambda 1 x1 plus x2. So, we can write down as minus lambda 1 1 0. Now, x2 dot minus lambda 1 x2 u. So, the terms of x1 and x3 are 0 in x2 dot, and similarly we find that the term of x3 is 0 here. That is why here we are written lambda 1 1, but in this case x2 dot the term of x1 and x3 are 0. So, we write 0 minus lambda 2 0, and lastly x3 dot equals to minus lambda 3 x3 plus u. So, we can write down as 0 0 minus lambda 3 plus, this is x, x1, x2, x3 plus just here for x1 dot there is no terms of u. So, we write 0, but as far as x2 dot is concerned, that is term of u, that is u is not 0. So, we write 1, and similarly for x3 dot we will get a term of 1. So, x dot equals to ax plus bu. So, we represent at x dot equals to ax plus bu. A is this lambda 1 1 0, 0 minus lambda 2 0, 0 0 minus lambda 3, and whereas b is 0 1 1. So, state equations we have determined. Now, we have to determine the output equations. So, for output equations, now about output equation. So, here output equation y of s equals to, right, b3 into u of s plus, you just see here, second is c1 into x1 of s, c2 into x2 of s, c3 into x3 of s. Now, here we apply again inverse Laplace transform. So, we will get y equals to c1 into x1, c2 x2, c3 x3 plus b3 into u. So, we have got this as output equation c1 x1, c2 x2, c3 x3, b3 u, and we have seen that here we got x1 dot, x2 dot, x3 dot, lambda 1 here is actually we write as lambda 1, not lambda 2, actually we have taken it is actually lambda 1. So, lambda 1 0 0 0 lambda 3 x1 x2 x3 0 0 1 u, because here this particular block, this called as Jordan block, and here in this block this lambda 1 are the repeated, and again you find that in this particular case you have 0 and 1 is there, but if you see the actual canonical form, actual diagonal canonical form, here we will get 0, here we will get 1, but in Jordan that 0 and 1 has been interchanged, you can easily observe here. Now, here y of s equals to b3 u of s, c1 x1 of s, c2 x2 of s, and c3 x3 of s, and now y we have written like this, y equals to c1 c2 c3 x1 x2 x3 plus b3 into u. Now, this is an output model, this is C matrix and this is a D matrix, C matrix and D matrix. And why here D has come? D has come because if you see your original transfer function is a proper transfer function, and in many of our previous classes we have already seen that whenever there is a proper transfer function, there exists a term of B. So, in this way we have determined the model, state space model in Jordan canonical form. Now, after this model has been determined, our main purpose is to verify its performance. So, this performance can be verified through any software, we can use a MATLAB also. But before that we have to develop the model in Simulink. So, we are developing now a block diagram of a Jordan canonical form. Now, how to develop the model? Last time we have seen the order of the system or number of states which are present equals to number of indicators. So, you will find that the order is 3. Therefore, how many indicators we required? We required 3 indicators. So, first of all what we do? First of all, write the equations and then we try to formulate the model. So, already the equation we have derived, I am writing down the equations. Lambda 1 equals to x1 dot equals to lambda 1 x1 plus x2, x2 dot that is equals to minus lambda 1 x2 plus u, and x3 dot equal to minus lambda 3 x3 plus u. See the equations: x1 dot lambda 1 x1 plus x2, x2 dot lambda 1 x2 plus u, x3 dot equals to minus lambda 3 x3 plus u. Now, we have to develop the model. So, first of all we use one integrator. So, one integrator for these equations. So, here I am using an integrator like this. Now, here this is x1 dot and now here is x1 and now this x1 dot equals to minus lambda 1 x1, that is we have to show here minus lambda 1 and now here we have to show x1. So, x1 dot equal to minus lambda 1 x1 plus x2. So, I am showing x2 here. Now, about the second equation is x2 dot equals to minus lambda 1 x2 plus u. So, here again we have to use one integrator. So, I am using one integrator here and here I am showing, because of this integrator we will show x2 dot and now here I am using again a summation block. So, here x2 dot equal to minus lambda 1 x2 plus u. Now, about the third, x3 dot equals to minus lambda 3 x3 plus u, that means here also we have to use another integrator. So, here I am showing integrator like this. Here is another integrator, summation block. So, here this is x3, here x3 dot and here we are showing minus lambda 3. So, we have shown lambda 1 minus lambda 1 minus lambda 1, then another is minus lambda 3 and here x3 dot equal to minus lambda 3 x3 plus u. Now, here u, this is also u, this is also u. So, it is so we can combine it. So, all the states we have shown. So, all these states, that means this equation we have represented here, but complete statement model involves state equation as well as the output equations. So, here also we have to show output equation. So, what is output equation? Y equals to C1 x1 C2 x2 C3 x3 B3 into u. Therefore, now here we will show output y. So, which signal is coming here? That is C1 into x1, second is C2 into x2. So, C2 into x2. So, let us say this is x2. So, here we take C2 and we connect here. Now, about C3 into x3. So, we will connect C3 here and this is output. So, this part we have completed. Y equals to C1 equal to x1, C2 x2, C3 x3, but now here is another term B3u. Now, we have to connect B3u. So, u is there. So, what we do simply, we will connect the block B3 into u. So, this is u. So, we will find that we have determined the state space model in Jordan form, when Jordan form is when there are repeated eigenvalues. So, whatever we have seen, so I will again explain in a systematic manner So, for that purpose what I have done here, I have taken the same transfer function ys by us equals to bn sn b of n s minus 1 b1 s plus b naught s plus lambda 1 q s plus lambda q plus 1 s lambda q plus 2 s lambda n. That is, this is the generalized form. Example we have taken the third order only, and now here I have shown q are repeated poles. It can be 3, 4, 5 and even, but finally it comes lambda n. Same thing, suppose q equals to 2, n equals to 3. So, here b3 s cube, b2 s square, b1 s b naught, s cube, a2 s square, a1 s a naught. The transformation we have described earlier, same thing is here. Now, above equation can be written as b3 s cube, b2 s square, b1 s b0, and now here lambda 1 is the repeated eigenvalue. Now, above equation can be written in simplified form as b3 c1 s lambda 1 square, c2 s lambda 1, c3 s lambda 3. Now, we have solved this equation, y of s equals to b3 into u of s, c1 s plus lambda 1 square into u of s, c2 s plus lambda 1 into u of s, c3 s plus lambda 3 into u of s, and finally y of s equals to b3 u of s, and this u of s plus lambda 1 square we have taken as x1 of s, c2 is here, u of s plus lambda 1 we have taken as x2 of s, then c3 u of s divided by s plus lambda 3 we have taken as x3 of s. Now, again from above equation we write this x1 of s, same thing, 1 upon s plus lambda 1 square into u of s, x2 of s equals to 1 upon s plus lambda 1 into u of s, x3 equals to 1 upon s lambda 3 into u of s, and now for this equation we apply inverse Laplace transform, and finally we have got result x1 by x1 of s by x2 of s equal to 1 upon s plus lambda 1. So, x1 dot lambda x1 plus x2, x2 of s equals to 1 upon s plus lambda 1 u into u of s we write as x2 dot minus lambda 1 x2 plus u, and third x3 of s equal to 1 upon s plus lambda 3 into u of s. So, we have written as x3 dot equal to minus lambda 3 x3 plus u, and finally this has been written in the state space model as x1 dot x2 dot x3 dot equal to minus lambda 1 1 0, x2 dot 0 minus lambda 1 0, x3 dot equal to 0 0 minus lambda 3, x1 x2 x3, and you see here 0 1 1. In a discussion I have told that the 0 has been appeared here in a diagonal canonical form, but in case of Jordan canonical form this instead of 1 here we have comes, instead of 0 here comes 1, and here instead of 1 0 has come, and this particular block is called as Jordan block. And again finally output y equal to c1 c2 c3 x1 x2 x3 plus b3 of u. So, now we will see the block diagram of Jordan canonical form. So, 3 integrators, integrator 1, integrator 2, integrator 3, then here lambda 1 here minus minus, then here is lambda 3 eigenvalues, this lambda 1 lambda 2 are repeated eigenvalues, then c1 c2 c3 the elements of the output matrix, then here b3 which concern with the coupling matrix D input, and here is output y of s. So, all theory we have seen. Now, we solve one example, very simple example. So, here I have taken a ys by us equal to 2s plus 4 divided by s plus 3 whole square. So, how to solve this problem? As I told that this has repeated pole s plus 3 whole square. So, here we have to use the concept of the partial fraction expansion. So, what we have done, 2s plus 4 s plus 3 square equal to c1 divided by s plus 3 square plus c2 s plus 3. Now, we have to solve it. So, ys by us equal to 2s plus 4 s plus 3 whole square equal to c1 plus c2 s plus 3 into s plus 3 square. Now, what we do, this equation, this part we will compare. So, 2s plus 4 equal to c1 plus c2 s plus 3. So, now we have to solve it. So, what we will do, we replace s equals to 0 in this equation. When we replace s equal to 0 in this equation, what will happen? It becomes 4 c1 and 0 means 3 into c2. So, we will get equation 4 equal to c1 plus 3 c2. Next, now what we do, we replace s equal to minus 3 in this equation. So, when we replace s equals to minus 3 equation, this will become 0. So, what we will get? This 3 minus 6 plus 4, finally we will get C1 equal to minus 2. And now what happened? We have got C1 equals to minus 2, we also required the value of C2. So, what we will do? We replace C1 equals to minus 2 in this equation and we will get C2 equal to 2. Then y by us equal to minus 2 divided by s plus 3 square plus 2 divided by s plus 3. Now, we will solve it. Y of s equals to 2 s plus 3 whole square u of s plus 2 s plus 3 into u of s. What we have done? Now, what we have to do? U of s plus 3 square we will write as x1 of s, and then u of s plus 3 we have to write as x2 of s. Therefore, what we will get? Y of s equal to minus 2 x1 of s plus 2 x2 of s, and this y of x1 of s equals to 1 by s plus 3 whole square into u of s, x2 of s equal to 1 upon s plus 3 u of s. So, you will find that again this equation difficult to solve by inverse Laplace transform. So, what we are doing here? We are dividing x1s and x2s. So, when we divide x1s by x2s, what will get? 1 upon s plus 3. Now, you cross multiply it. So, after cross multiplication, what will get? We will get x1 dot equal to minus 3x1 plus x2, and x2 dot x2 of s equal to u of s plus 3. Again after cross multiplication, what will get? x2 dot minus 3x2 plus u. So, two state equation we have got. So, x1 dot x2 dot, then A matrix minus 3 0 0 minus 3, and here 0 1, and y equals to minus 2 2. This is the C matrix, this is A matrix, and here is the B matrix. Here there is no D matrix because this transfer function is strictly proper transfer function. Okay. Now, we will see here x1 of s divided by x2 of s equal to 1 upon s plus 3 x1 dot minus 3 x1 plus x2, x2 dot x2 of s equal to u of s plus 3, that equals to x2 dot equal to minus 3 x2 plus u. Now, we have to represent the equation. So, we will write as x1 dot equal to minus 3 x1 plus x2. So, here minus 3, and here instead of 0 we will get 1. So, x1 dot equals to minus 3 x1 plus x2 and 0 u, here out 0 u, and here x2 of s equal to u of s by s plus 3 will write as x2 dot equal to minus 3 x2 plus u. So, we write as x2 dot equal to 0 0 into x1 minus 3 x2, whereas term of u has come, and finally y equals to minus 2 to x1 x2, that is 2 x1 plus 2 x2, and here 0 into u, d is 0. Now, these are the references. Thank you.